Hello, Chem 1. In Unit 8, we've learned to determine the Lewis structure and the shape of a covalently bonded molecule. Today, we're going to look at what happens when we have two atoms within the molecule that do not share electrons equally. Let's get started on bond and molecular polarity. Before we get to molecular polarity, we have to start with bond polarity. Bond polarity is just a numerical way to quantify how unevenly or how electrons are being shared between two atoms. Remember back in Unit 5 when we talked about strong and weak atoms, and we said that strong atoms have a higher electronegativity or a greater ability to pull electrons toward themselves when they're in a bonded situation. What this means is if you have a strong atom paired with a weak atom, even if they're in a covalent bond, they may be sharing electrons, they just might not share equally. Let's run through a couple scenarios. Scenario 1 would be if electrons are equally shared. This would be if their electronegativities are very similar. The difference between their electronegativities would be less than 0.4, meaning you'd take their two electronegativities, you'd subtract them from one another, and if they're less than 0.4, we would say they're sharing evenly and call this a nonpolar covalent bond. We would say there's no charges present. There's not a positive or negative end. Case number 2 would be if the two atoms do share electrons unequally. And if we subtracted their electronegativities, we'd get an answer between 0.4 and 1.7. What this means is that one atom is stronger or better at pulling electrons toward itself, and therefore we would form a polar covalent bond. This would result in a positive end and a negative end of the bond. We call these positive and negative ends dipoles. Here's a representation of a polar covalent bond. Fluorine is much more electronegative than carbon, and so because of that, it's going to pull electrons, even bonded electrons, toward itself, and therefore fluorine will be the negative end of that bond because electrons are negative. Carbon, therefore, would have more positive charge because it's losing electrons, they're shading toward fluorine. Case 3 typically happens when you have a metal and a nonmetal, two things that have very different electronegativities. When you subtract those electronegativities, you're going to get something that's greater than 1.7. When that happens, instead of sharing the electrons, one atom is so strong, the nonmetal, that it just takes the electron from the metal. And we already studied this in Unit 6. This is called an ionic bond. That would leave you a negative anion and a positive cation that would attract to one another. So if you look here, we can kind of see an electronegativity difference scale. We can see that if we have something that is less than 0.4, that's going to be a nonpolar covalent bond. A lot of times when things are diatomic, or things are bonded to themselves, that'd be nonpolar covalent, because if you subtract those two electronegativities, they're the same, you'd get 0. Then if we get a difference in electronegativity in between 0.4 and 1.7, we get a polar covalent bond. Hydrochloric acid would be an example of this. And then finally, if we have complete donation or transfer of electrons because of a large electronegativity difference of above 1.7, we're going to get an ionic bond. Now you're going to want to get out your green reference sheet. On that sheet, there's a periodic table that has all the electronegativities for every element. We can use that to calculate what type of bond these substances will make. So if you look at carbon on that sheet, you see that it has an electronegativity of 2.5. And hydrogen has an electronegativity of 2.1. So if we subtract those, we get a difference of 0.4. If you remember our scale, we said if something has a difference of 0.4 or below, that would be a nonpolar covalent. So we would classify this bond as nonpolar covalent. And we have NaCl. Now, you probably know that sodium's a metal and chlorine's a nonmetal, so that's going to be an ionic bond. But we can also do this mathematically. Sodium is 0.9 and chlorine is 3.0. If we subtract those, we would get 2.1, which is greater than 1.7. That means this is an ionic bond. Oxygen's 3.5, hydrogen's 2.1. Subtract that, we get 1.4. So now we're in between that 0.4 and 1.7 range. So this is a polar covalent bond. With a polar covalent bond, you'll have a negative end and a positive end. The negative end is always going to be the stronger atom with the greater electronegativity pulling electrons toward itself. So in this case, the oxygen would be negative and the hydrogen would be positive. Silicon has a electronegativity of 1.8. Hydrogen is 2.1. This is a difference of 0.3. So this is a nonpolar covalent bond. This is kind of different because silicon is a metalloid. But based on these electronegativities, we can see what kind of bond it would make. Carbon is 2.5. Oxygen is 3.5. That gives us a difference of 1, which means this would be a polar covalent bond. So from this point forward, if you ever want to figure out what kind of bond it is, all you have to do is subtract the electronegativities of the two atoms in the bond. So based on what we just talked about, we talked about bond polarity, the polarity between two atoms that are making a bond. But we've been dealing with molecules where there are multiple bonds taking place. So the question becomes, how does each bond polarity affect the entire molecule? That's what we're going to talk about next. All right, case one. Case one is if you have nonpolar bonds, it has to be a nonpolar molecule, meaning that if the bond isn't polar, there's no way for this molecule to be polar. So if you have nonpolar bonds, it will always be a nonpolar molecule. The next case would be if you have bonds that are polar. In this case, the molecule could be polar and it could not be polar, but it'll depend on the shape whether you have polarity or not. There's a couple different ways to determine molecular polarity. The first part of this is to do the things we already know how to do. Draw a Lewis structure, determine the shape, then look at the bond polarities of each bond. Then you can label the partial charges, which end is negative, which end is positive. At that point, you can do something called a straight line test. A straight line test is if you can draw a straight line through the central atom that separates the positive from the negative end. If you can do this, then it's a polar molecule. If you can't do this, it's a nonpolar molecule. Let's do a couple of examples, and I think that'll help you understand this a little better. So if you look at methane, we've drawn this several times now. We know that we're going to have hydrogens on all the sides of carbon here. This would have 8 valence electrons, and we've placed 8. The hydrogens are stable, the carbons are stable. So this is going to be a tetrahedral, and we need to figure out what kind of bonds they have. Carbon is 2.5, and hydrogen is 2.1. That gives us a difference of 0.4, meaning that this methane has nonpolar bonds. The second that you identify this as nonpolar bonds, you know it's a nonpolar molecule, period. You can't get a polar molecule from nonpolar bonds. It can't happen. So we're done. Nonpolar molecule. The next one is H2O. We know that when we originally draw our Lewis structure, we would draw it like this. It also has 8 valence electrons. And if we draw it in the correct shape, because this has 2 lone pair, we know that this is going to get pushed into a bent configuration. Water looks like this. So now let's take a look at the bonds within water. We have 2 bonds that are an O bonded to an H. O is 3.5, H is 2.1. That's a difference of 1.4. That means we have polar covalent bonds. The question becomes, do we have a polar covalent molecule? So we need to figure out where the negative end is, where the positive end is. Well, oxygen is more electronegative. That means this end of the bent molecule is going to be positive, and the hydrogen end is going to be more negative because electrons are moving toward that hydrogen end. The question becomes, can I draw a line that separates the positive from the negative? Well, if I draw a line right here, guess what? I just separated the positive from the negative end, so that means this is also a polar molecule. The next one here is carbon dioxide. Carbon dioxide we've drawn a couple times. I'm going to hurry through this. It will look like this at the end with a double bond on both sides. This central carbon has 2 domains, 1, 2. And there's no lone pairs. Whenever we have 2 domains and no lone pairs, we know that this is going to be linear. Oxygen is 3.5, carbon is 2.5, and that is a difference of 1.0. So this has polar covalent bonds. The question becomes, is it a polar molecule? These oxygens are more electronegative, and the carbon will be more positive. So the question is, can I draw a line through this carbon that'll separate the positive from the negative? Here's the thing, I can't. Because this is very symmetrical, there's no line I can draw to separate them. And this makes sense if you think about what's going on. Each oxygen on both ends of the molecule are both pulling with great strength, but no one's winning the tug of war. Because they're evenly matched, the overall charge is nonpolar. So we'd call this a nonpolar molecule. There's more examples of these that we'll do when we fill out the chart. There are also other ways to figure out which molecules will be polar and which ones will not be. We'll get to that when we fill out the chart. Take some time to practice these in identifying the bond polarity and molecular polarities on the activity that you have today. Keep working hard. We will see you soon.